Hi, my name is Martin and I'm talking about the minimization of random hypergraphs. Our original motivation came from the following observation in data profiling, which is the mining of metadata from relational databases. One type of such metadata are so-called unique column combinations. These are sets of columns such that the value combinations there appear at most once. So if you tell me that the name is John Doe and he lives in UKW1K, I know that you are talking about the third row and the third row only. Also, it is known that these UCCs are the hitting sets of different sets of pairs of rows. So if you look at this pair and look at those attributes or those columns in which they differ, then every UCC has to contain either the address, the city, or the area code, because otherwise this pair would be indistinguishable. The next pair differs in every column, so this doesn't tell us anything. Or a bit more formally, the new difference set is a superset of one that we already know, so it is redundant. The next pair has some new information, but a lot of other pairs like this and that do not. And I shortcut this process here because the only other pair that contains new information is that one. So a typical preprocessing is to compute these difference sets and discard the supersets. The remaining inclusion-wise minimal edges are called the minimization of that hypergraph. And the observation in practice is that these minimizations are very small, much smaller than the original databases. And we wondered, why is this the case? On one hand, this is a very interesting property. On the other hand, if we know that the minimization of a hypergraph is small, we can compute it faster. So there are some worst case lower bound known based on the orthogonal vectors conjecture, but if we know that the minimization is usually small, we can beat these lower bounds in the average case. For an average case analysis, we need a distribution. For mere graphs, a lot of random models are known. Most prominently, the Chernoff-Hoefiding graphs or closely related Gilbert graphs. These are maximally random in the sense that you only specify the number of edges and the number of vertices and then draw one graph at random meeting these constraints. In other words, the Chernoff-Hoefiding graphs are the maximum entropy distribution on graphs with n vertices and m edges. And the same is true for Gilbert graphs for an expected number of edges. You want this maximum entropy because you only specify those graph parameters you need and exclude any outside bias for the rest. So you really want that. Unfortunately though, there are only a few non-uniform hypergraph extensions known. We need non-uniformity in the sense that different edges may have different numbers of vertices, because otherwise inclusion cannot happen. So uniform hypergraphs are not interesting for us. In our model, we take the maximum entropy distribution on multi-hypergraphs with n vertices and m edges with an expected edge size of p times n. So we do allow different sized edges. And multi-hypergraph here means that we also allow multiple copies of the same edge, because this is closer to our original difference sets, where also some pairs may have the same attributes in which they differ. In the end, this is equivalent to sampling m subsets of an n-element set and including any vertex independently with probability p. And the question is, how large is the expected size of the minimization of that hypergraph? So the number of inclusion-wise minimal edges. Indeed, we were able to give tight bounds on this expectation in terms of the three parameters n, m, and p. And what you see here is a visualization of that size as the number of edges increases. This is plotted for a rather large small number of vertices, but these features are even more prominently as n increases. And what you see here is that in the beginning, the minimization quickly grows with the number of edges until a certain peak. But if you include more edges, the minimization in fact goes down, so fewer edges are minimal here. And this decay is exponential in M. But also this peak here, if you look more closely, it happens around 1,000 edges or so. But the number of minimal edges is only just over 100. So even in this peak, the minimization is much smaller than the underlying hypergraph. And this gives a good explanation why we can expect minimizations to be small. Also, our analysis discovered a phase transition happening in this minimization around the time M reaches 1 divided by 1 minus p to the 1 minus pn. In this plot, that would be somewhere very close to the origin here, so you wouldn't see anything. So a better visualization is that you define alpha to be the linear scaling of the exponent of M, and then look at the size of the minimization as alpha increases from 0 to 1. And since alpha is essentially log m divided by n, the plot on the right side is a log-log version of the one on the left side. And additionally, it's independent of the number of vertices n. And what you see here is until alpha reaches 1 minus p, you have a linear growth in alpha, which in a log-log plot means you have a polynomial growth in terms of n. And in fact, we were able to show that this polynomial is linear. So as long as the number of edges is smaller than this transition point, the minimization grows linearly in the total number of edges. If we go beyond that point, we at first continue to grow, but sublinearly in alpha and thus subpolynomially in M until this peak. And once we go over this peak, the minimization really comes crashing down super fast. In our paper, we also give a closed form for the intermediate ranges between 1 minus p and 1. It's of this form. It uses the perplexity from information theory together with this correction term, which essentially states that in this area, the growth is even slower than what you would expect from the pure perplexity. And in fact, once we reach alpha equal to 1 or m equal to 1 divided by 1 minus p to the n, then the minimization essentially consists of a single edge, which is the empty set. As a corollary of our analysis, we were also able to pinpoint down this peak exactly at alpha equal to 1 divided by 1 plus p, with a value of 1 plus p to the n divided by square root of n. So indeed, this peak is much smaller than the size of the underlying hypergraph that corresponds to it. And the way to prove this theorem was to establish a close connection between the minimization and the probability that a binomial random variable deviates largely from its expectation. Because then any bound on the binomial distribution function transfers back to a bound on the minimization. This transfer happens with some techniques from combinatorics and information theory. But really the main issue here was that the known bounds on the binomial distribution are not sharp enough to derive tight bounds on the minimization. So we had to find out how likely is a binomial random variable deviating from its expectation. And for that, we estimate the probability that x is smaller than some small x times n in terms of this small x. And we use the Kullback-Leibniz divergence, again from information theory. The best known upper bound of this type is the so-called Chernoff-Hoefiding Theorem, which states that this probability is smaller than 2 to the minus the divergence times n. This is also the basis of most of the known Chernoff bounds in the literature, which might be weaker in some cases, but more practical. So this is really the core of Chernoff bounds. If you apply Stirling's approximation to the largest subprobability, you get a lower bound of almost the same type, but for this additional factor of essentially 1 divided by square root of n. So these bounds are not tight. There's a square root n gap, and we close it down to a constant in order to derive tight bounds also on the minimization. In other words, we show that as long as x is strictly between 0 and p, the probability behaves essentially like the lower bound. So 2 to the minus the divergence times n divided by square root of n. And this even holds true if x depends on n, as long as it is bounded away from these boundaries 0 and p. The way to prove this is to combine a ratio on the distribution function for the binomial distribution divided by the probability mass function, and combine this with the perplexity bound on for binomial coefficients. So in the end, we were able to tighten Chernoff-Hoefiding and from this derive tight bounds on our minimization. We analyzed the minimization of maximum entropy hypergraphs, which had some interesting implication for large databases as well as fine-grained complexity. And we discovered a phase transition in this minimization happening. And finally, we gave new tight bounds on the binomial distribution, which might be of interest in other areas of probability beyond the treatment of hypergraphs. And with this word, I thank you for your attention.